Alright， 我是 B123100022郭成汉 and I'm going to derive the first question. Yeah, the first question. Alright. And this is the Planck's law in frequency form. Yeah, goes to this. And this, the frequency equals to the light velocity divide the wavelength. Okay, and we transform to wavelength form. It looks like this into this. Okay, and we're finding the maximum energy density. We're going to like this. In order to finding the maximum energy density, so this have to equal to 0. Yeah. 微分怎么讲？我忘记了。
Derivative.
We have derivative the
Equation into 0.
Equation into 0. Yeah. So this leads to transcendental equation of the form like this, and when we calculate this, and we know x will almost equal to 4.965. All right, and we put into the equation, Wheeler's law. 然后你说那个叫什么？
就像我刚刚说的嘛，那个 given equation， 因为
we throw into the given equation the Wheeler's law, and we can know that this into C.
Okay.
Right. I'm going to describe in detail an experiment in which the wave character of the particle is demonstrated, and this is the 第二题。我是 B123100022郭成汉。Okay. Hello everyone. Today we are going to show an experiment that demonstrates the wave nature of particles using ultra cold atoms in an interferometer. 是这样念吗？Okay. Unlike the traditional double slit or electron diffraction experiments, this one uses both Einstein condensate or BEC to reveal the wave behavior of atoms. First, step 1, cooling atoms to form a BEC. First, we take a cloud of atoms, for example, rubidium-87, and we cool them down to near absolute zero using laser cooling and evaporative cooling techniques. At these extremely low temperatures, the atoms lose their individual identities and form a single quantum state, a Bose-Einstein condensate. Okay, this condensate acts like a giant matter wave with long coherence. Step 2, splitting the wave packet. Next, we use carefully timed laser pulses, such as Raman beams, to split the atomic wave packet into 2 parts. This is similar to how a beam splitter works in an optical interferometer. Each part travels along a different path, carrying different phases. Step 3, recombine the paths. After some time, we recombine the 2 atomic wave packets. If the atoms truly behave like waves, we should see interference patterns depending on the phase difference between the 2 paths. Okay. Step 4, observing interference. Finally, we use a high-resolution CCD camera to image the resulting atomic distribution. What we observe are interference fringes. Just like light waves create a Michelson interferometer. interferometer. This proves that atoms, which are massive particles, exhibit wave behavior. Okay, and our conclusion and interpretation. This experience clearly shows that matter is not only made of particles, but that these particles have wave properties. The interference patterns can only be explained if the atoms act like waves and interfere with themselves. This result supports the idea of wave-particles duality, a fundamental concept in quantum mechanics. Atom interferometry is not just a cool demonstration. It is also used in modern technologies, such as quantum sensors, atomic clocks, and even tests of general relativity. Okay, thank you for watching, and this is my report.
Okay, my name is Li Sunwei, B 09300050. Okay. In this question, I need to describe in detail an experiment in which the particle character of a wave is demonstrated. Okay. We need to demonstrating the particle nature of a wave using single photon detection. In this video, we will describe an experiment that demonstrates the particle nature of a wave, specifically light. Instead of the usual photoelectric or Compton effect, we'll look at a modern and fascinating setup, the single photon detection experiment. The step 1, classically, light is understood as an electromagnetic wave, a continuous field that should transfer energy smoothly over time. But quantum mechanics tell us that light energy is quantized and is delivered in discrete packet called photons. The step 2, setting up the experiment. In this experiment, we use a special light source called a single photon source. This could be quantum dot or a non-linear crystal that performs spontaneous parametric Dow conversion, producing pair of photons. One photon is used to trigger the system, while the other is sent toward a single photon detector. The step 3, detecting light one photon at a time. Now we reduce the intensity of the light beams until at any moment there is no more than one photon traveling in the system. We use a single photon detector such as an avalanche photodiode or a superconducting nanowire detector. Every time a photon hits the detector, it causes a tiny electric pulse, or what some call a click. The step 4, observing discrete click. Instead of detecting a continuous signal, we observe discrete random clicks, one at a time. Each click represent a single photon being absorbed, a clear sign that the light energy is arriving in individual particle light units, not as a smooth wave. The interpretation of this experiment proved that light, even though it behaves like a wave in interference and diffraction, can also behave like a particle. These particle photons are indivisible and their energy is quantized. There is no half click, no split detection, only full detection of a whole photon. Its application and significance is this kind of experiment forms the basics of quantum optics and is used in technology such as quantum cryptography, quantum random number generation, and entangled photon source. Thank you.
So this is the question number 4. My name is Li Sunwei, B0993100050. So this is the given equation wave packet, where here, so we can substitute the second formula into the first formula, and we got this. Then we need to rearrange the exponential form into this, and then we found that this can use the Gaussian integral to solve it. Then we got this, and then we got the center of the wave packet move with constant velocity here. We proved that the probability density, which can also be Gaussian. Next, we need to find the expectation value here. The first line here is the definition of the expectation value of the position operator x at time t. It's the integral over the all space of the position x multiplied by the probability density of finding the particle at the position. The second line, this is a specific case of Ehrenfest theorem. It states that the time evolution of the expectation value of position, when multiplied by the mass m, is equal to the expectation value of momentum. And then 3, the third line, this is the definition of the expectation value of the momentum operator. And we calculate into this. And this p equal to p0, this follows from the fact that the momentum space wave function given in the problem is a Gaussian distribution centered at p0. The expectation value of the Gaussian distribution is its means, which is case is p0. Then the result of integrating the expectation velocity with respect to time. This shows that the average position of the wave packet moves with a constant velocity v over time. Alright, this section focusing on the calculating uncertainty in position, denoted as this one. At the first line, this is the definition of the variance of the position, which represent the square of the uncertainty in position. The second line here, this shows the initial wave function at time t equals to 0 as a Gaussian distribution centered at x0. The third line here, this relates the initial standard derivation in position sigma x to the initial standard derivation in momentum sigma p, based on the minimum uncertainty principle for Gaussian wave packets. And then this extracts the standard derivation in momentum sigma p from the momentum space wave function. This substitutes the expression for sigma p into the relation from the third line to find the initial standard derivation in position sigma x at t equals to 0. Then calculate the initial variance square of the standard derivation in position at time t equals to 0. This shows how the variance in position evolves with time. Sigma x is the initial variance, and the second term accounts
for the spreading of the wave packet due to different momentum components. This concludes that the uncertainty squared in position at time t is equal to the initial uncertainty squared plus a term that increases quadratically with time. This demonstrates the spreading of the wave packet as time progresses. Thank you.